Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is just to go through a quick example of a simple DC circuit problem. So the example that I'm making up here is something that came to my mind here from things we used to do when I was a kid. When I was a young kid, we used to make basically a frame that went over the front of a boat, and the frame would have these bulbs connected to it, right? And I would typically buy 3 or 4 bulbs, and I'd hook them to the frame, and I'd run them off a battery. And these bulbs would go underwater, and you would motor around the lake and look for fish and turtles and all sorts of cool stuff. So in this example here, imagine we've got this 80-watt bulb, and it's important to realize that this is a bulb designed to run off a 12-volt source. So this is a bulb that you would get at an RV store or something like that. And the other one here I'm going to imagine is a 40-watt bulb in this example. We're going to try to calculate a couple things. First, we're going to calculate the resistance of these bulbs, and second, we're going to calculate the current through each bulb and the current coming from the battery if these guys are hooked up in a parallel combination. So let's start with the resistance. All right, so these 80 watts, the 80 watt and the 40 watt, these are units of power. And in electrical problems, power is equal to current times voltage. It's also equal to I squared R, and it's also equal to V squared over R. All three of these give power. Now, which one we use? It doesn't really matter. I'm going to go ahead and use this one, that the power given for a bulb is equal to current times voltage. All right, for the 80-watt bulb, right, the power would be 80 watts. The current I don't know, but this bulb is designed to run off a 12-volt source. Now, if this were a light bulb for home use, the AC home voltage is around 120 volts. That'd be a different problem. But in this example, these bulbs are designed to run off a 12-volt. So the current we can expect for this bulb is going to be, let's see, 80 divided by 12. We can expect this to draw about 6.7 amps. Okay. For the 40-watt bulb, same equation. The power is 40 watts, and that's equal to current times 12 volts. And in this example, that power is going to be 40 over 12, which is going to be half of what it was before, 3.33. I'll just say 3.3 amps. So there's the power dissipated by each of these, there's the current that each of these bulbs is going to draw. Okay, resistance. I can get at the resistance basically the same way using this form. Let's see. Power is equal to current squared times resistance. So for the 80-watt bulb, we have the 80 watts is equal to, and now we know the current that bulb is going to draw, 6.7 amps squared times R. So the resistance of this bulb we would get by taking 80 and dividing by 6.7 squared. And I get about 1.78 ohms. And then for the 40-watt bulb, we have 40 watts is equal to, this animal is going to draw 3.3 amps, and that's squared times R. So again, that's power equals I squared R. And if we solve that for R, I get about 3.7 ohms. All right. So one thing to notice, you'll notice that as the resistance gets higher, power goes down, and that's a very standard pattern. As the resistance of a circuit gets higher and higher and higher, current goes down. And if we look right here, power is I squared R. Power is very highly dependent on current. Right? Now, I now know the current that's going to go through each of these. This bulb, 6.7 amps. And this one was 3.3 amps. And now I'm going to talk about the current coming from the battery. In order to do that, what I'm going to do is I'm going to draw what's called a circuit diagram. All right, so let's see. I'm going to get rid of stuff I don't need. Don't really need any of this anymore. All right, So imagine that these are hooked up in parallel. A parallel hookup would look something like this. We'd wire it. The wire would go through one bulb, right, and then to the other. Then they would come back together. It doesn't matter where I hook up to this. Typically, they would go through some sort of switch and then to the lower potential terminal of the battery, the negative potential. Now, when the switch is closed, we're going to have a current that's going to be going here. I'm going to call that current. I'm going to put a B for battery, and that's got to be the same as this part of the circuit. Right? You can't have current coming out of one terminal and nothing going in. If you go back and watch my video about batteries, I'll explain a little bit about why. It just isn't possible. You know, whatever current we have coming out, we have to have the same current coming in. These current directions are assuming positive charge carriers. Now, at this point right here, there's kind of a divvying. Some of this charge goes this way, some this way. So now we have two different currents. So I'm going to draw them and call this maybe, how about I1 for the current through what I'm calling bulb 1 now. Then we're going to have another current here, I2. Now the I1 I've already found, 6.7 amps. The I2 I've already found, 3.3 amps. Now, although I don't really need it for this problem, I'll talk a little bit about drawing the actual circuit diagram. This is a sketch for what the circuit might look like. The actual circuit diagram for this sketch might look something like this. So this is the symbol for potential difference. That would be the potential difference of the battery, in this case 12 volts. Then this is the symbol for resistor. I'm going to call this R1. That would be representing this light bulb. And then here's another resistor symbol for this light bulb, and I'm going to call that R2. And then this goes around to here. So here's what the circuit diagram might look like. The exact shape of it, you know, not really important, but it does have to have the following properties. You know, we need this symbol here for potential difference. The long terminal represents the positive lead, the short terminal the negative lead. You'll notice that the wire splits here and here. Right? In my picture, there's my split. The current that I called IB from the battery, that would be the current in this branch right here. So I'm going to draw that in. And it's the same thing in this bottom half of it. So in this picture, that would be the same. Again, whatever goes in the battery has to be coming out, so these have to be the same. Then the current I1 in this picture is here. I can draw it anywhere along this branch. It doesn't really matter where I draw it, anywhere in this branch. And then I2 here. And again, I can put that I2 anywhere in this branch. And to calculate the last thing here, we want to get that current coming out of the battery. Now you'll notice right at this junction right here, you'll notice that in my picture I've got this IB current from the battery going in and the currents I1 and I2 going out. And that means there's a simple arithmetic relationship between them. The current coming from the battery is equal to the sum of I1 plus I2. In this case, that's going to be 6.7 amps plus 3.3 amps. And if we add these together, we get 10 amps. So this pair of bulbs should draw about 10 amps from the battery. Now, some comments about this problem. There are some things here, you know, I work this to what I would call rough approximation. The batteries themselves tend to have some internal resistance. So what happens is when you actually draw a 10 amp current, the voltage between these leads tends to drop a little bit. I used 12 volts in most of my calculations, but again, you know, the actual voltage varies a little bit battery to battery. So this is kind of an idealistic case. You know, I'll make other videos that work these in a bit more detail, but I think it, you know, for a general first example type of situation, this is just fine. So how did we find these? Well, I started with the following equations, right? So power can be written current times voltage, right? But remember Ohm's law is V equals IR. So, for example, if I put IR here, I get I squared times R. So power can also be written I squared times R. The other thing I can do is solve this for I and sub it there. And this would then read V squared over R. The reason for starting with these power equations is because in this example I was given powers, 80 watts and 40 watts. So that was a clue that that might have been a good place to start. Anyway, I hope this example helps. Have a great day.